Engineering is a discipline built on logic, precision, and the laws of physics. It's a science that solves problems, builds civilizations, and creates technologies that define our modern world. However, beneath the surface of this seemingly exact and calculated field exists a realm of mysteries, puzzles so baffling they defy even the sharpest minds and most advanced tools. These are the hidden enigmas in engineering where science, experimentation, and theory reach their limits. Welcome to a journey into the engineering mysteries science can't explain. In the next 2 hours, spread across 16 detailed parts, we will unravel the most baffling phenomena, the paradoxes and the weird anomalies that have perplexed engineers, scientists, and inventors for generations. We will explore inexplicable infrastructure failures, unexplained materials behavior, mysterious energy sources, unaccounted forces in fluid dynamics, and failures of machines that cannot be fully explained by known physics or engineering principles. This is not just about broken devices or errors. It's about questions that shake the very foundations of how we understand engineering itself. From bridges that collapse without a traceable cause, and materials that behave unpredictably under stress, to energy anomalies in systems and machines exhibiting unexplained properties. These mysteries challenge our knowledge, spark curiosity, and inspire new scientific inquiry. What makes these phenomena so confounding? Why do some experiments and real-world observations stubbornly resist scientific explanation? And could these enigmas hint at new, undiscovered laws of nature hidden within the realms we thought were thoroughly understood? This series will delve deep into documented cases, scientific studies, and anecdotal reports presenting the evidence and hypotheses while maintaining a skeptical yet open mind. It is a space where engineering meets the frontier of the unknown, where we question, investigate, and sometimes accept that some questions remain unanswered. This introduction sets the stage for an immersive exploration, holding nothing back and presenting the complex, sometimes eerie puzzles at the heart of engineering mysteries. Prepare for a blend of fact, speculation, and cutting-edge science that will captivate any engineer, scientist, or curious mind seeking to understand the limits of what we know and what remains elusive. Welcome to the first step into the realm where engineering challenges baffle reason and where the unexplained waits to be uncovered. Exploring the realm of engineering mysteries brings us straight to the very backbone of civilization, structures that defy our understanding. Engineering, defined by precision and predictability, encounters bewildering anomalies where structures crumble, oscillate, or resist all logic. In this part, we unravel baffling failures and perplexing phenomena in structural engineering that challenge the foundations of scientific certainty. Consider the infamous collapse of the Tacoma Narrows Bridge in 1940, often cited as the epitome of engineering failure, yet it remains a profound mystery in fluid structure interaction. Despite rigorous wind tunnel testing and calculations indicating safety, the bridge oscillated wildly in steady winds and violently twisted until it broke apart. Engineers initially failed to grasp the complex aerodynamic phenomenon called aeroelastic flutter, the bridge's oscillations which fed back energy into the structure, amplifying motion until catastrophic failure. Even decades later, full predictive models struggle to replicate the exact conditions that led to the collapse, leaving questions about the interplay of wind, structure dynamics, and material properties that still puzzle experts worldwide. Then there's the enigmatic behavior of concrete, the world's most widely used construction material, yet notorious for its mysterious degradation and unpredictable aging processes. While formulas predict shrinkage, creep, and cracking, historic Roman concrete structures boast legendary durability, resisting seawater erosion and earthquakes far better than modern mixes. Scientists have discovered unique mineral crystallization within the ancient concrete, but understanding how these nanoscale changes translate to long-term resilience challenges current materials science. Why exactly modern concrete fails, while older structures endure, remains an open scientific question, defying easy engineering solutions. Resonance. The tendency of structures to vibrate violently when exposed to specific frequencies is a classic engineering concept, but examples abound where actual behaviors starkly diverge from predictions. The London Millennium Bridge, upon opening, swayed laterally due to synchronizing pedestrian footsteps, a phenomenon termed synchronous lateral excitation. This self-reinforcing oscillation appeared smoothly and unexpectedly, forcing immediate closure and expensive retrofitting. Despite intensive research, accurately predicting pedestrian-induced resonance remains a challenge, exposing gaps in our understanding of human structure interaction and complex dynamic systems. Unexpected, unexplained crack propagation and sudden failures in high-stress components continue to elude definitive explanation. In critical domains, aircraft, nuclear plants, bridges, materials sometimes fail prematurely, even though measurements suggest stresses remain within safe thresholds. Acoustic emissions, vibrations, and microscopic defects occasionally signal impending failure, yet no clear predictive model reliably correlates these precursors. Why and how such silent, hidden damage progresses unpredictably resists full scientific clarity, making safety engineering a field of continuous vigilance and uncertainty. Seismic events reveal further mysteries. Engineers design structures to withstand earthquakes using principles of energy dissipation and base isolation. Yet recent powerful quakes have exposed unexpected structural responses, including torsional amplifications, dynamic soil structure coupling, and anomalous resonance shifts not anticipated by existing codes. These surprises compel the ongoing refinement of seismic design methodologies, as nature's complexity outpaces even our most elaborate simulations. Even steel, the backbone of skyscrapers and infrastructure, exhibits strange effects under certain conditions. Phenomena such as serrated yielding, strain aging, and delayed fracture introduce unpredictability to steel's mechanical response that defy classical plasticity theories. Long-term exposure to cyclic loads and environmental factors can trigger abrupt property changes compromising structural integrity without evident warning in material tests. Each instance blends multi-scale physics, from atomic lattice dislocations to macroscopic vibrations, complicated by environmental variability and nonlinear interactions. These structural engineering enigmas embody how complex real-world systems occasionally stumble beyond the grasp of idealized theory, reminding engineers that even the most trusted principles have limits. Through exploring these mysteries, engineers gain humility and inspiration, urged to innovate new modeling techniques, experimental methods, and interdisciplinary approaches. From re-examining foundational assumptions to inventing novel materials and monitoring technologies, we approach a future where today's mysteries become tomorrow's mastered knowledge. Fluid mechanics and energy systems stand as pillars of engineering mastery, governing everything from the flight of aircraft to the flow of blood, from power plants to ocean currents. Yet despite centuries of scientific advances, this domain harbors perplexing mysteries that challenge fundamental physical laws and computational predictions, creating puzzles where theory and experiment clash inexplicably. This part ventures into these anomalies, enigmatic phenomena, and fluid behavior and energy conversion systems that defy current understanding, revealing surprises at every scale and dimension. An enduring conundrum lies in turbulence, one of science's great unsolved problems. Turbulent flow, characterized by chaotic, multi-scale fluctuations in velocity and pressure, resists exact mathematical description despite governing Navier-Stokes equations being well known for nearly 2 centuries. Engineers experience turbulence as unpredictable drag increases, flow-induced vibrations, and energy dissipation complicating the design of everything from aircraft wings and pipeline systems to wind turbines and combustion engines. Attempts to model turbulence range from simplified Reynolds average Navier-Stokes RANS approaches to vast computational simulations, direct numerical simulation (DNS). Yet no general predictive model exists fully capturing intermittent bursts, coherent structures, or energy cascades observed experimentally. This leaves practical engineering reliant on empirical correlations and approximate models, perpetuating mystery around turbulence's intrinsic nature and control. Closely related are anomalous drag and lift behaviors in certain fluid flows. For example, the superhydrophobic effect, where surfaces dramatically reduce drag by trapping air, remains imperfectly understood at large scales, despite promising applications. Equally, the Magnus effect, enabling spinning balls to curve midair, still reveals subtle deviations that classical fluid dynamics models miss under varying conditions. Understanding these disparities holds critical implications for aerodynamic performance, sports engineering, and microfluidics. Fluid-solid interactions conjure further enigmas. Phenomena like vortex-induced vibrations (VAF) produce oscillating forces that can destroy bridges, chimneys, and marine risers. The exact onset conditions, amplitude growth, and pervasiveness of lock-in resonances elude full theoretical prediction despite advanced modeling and experiments. Similarly, hydroelastic instabilities, where fluid flow triggers elastic deformation, lead to flutter and divergence in slender structures like cables and pipelines, often with surprising thresholds defying linear assessments. In energy systems, thermal energy conversion, inefficiencies reveal mysteries in heat transfer and combustion dynamics. The quest for higher thermodynamic efficiency confronts unanticipated heat losses, combustion instabilities, and pollutant formation mechanisms not fully predictable, especially under transient multi-phase flow conditions within engines and turbines. Nano and microscale turbulence interactions, phase change kinetics, and flame front behaviors pose complex, unresolved engineering problems critical for cleaner and more efficient technologies. Some fluid flows exhibit counterintuitive chaotic behaviors, such as the Coanda effect, where jets curve around surfaces, or laminar turbulent transitions occurring unpredictably under nearly identical conditions, highlighting sensitivity to initial perturbations, defying deterministic expectations. These phenomena complicate design requirements for propulsion, HVAC, and chemical reactors. Unexplained energy anomalies in fluid dynamic systems also intrigue researchers. Certain configurations manifest emergent flows or pressure differentials hinting at yet undiscovered fluid structure interactions or subtle entropic effects. Experimental observations occasionally report unexpected energy inputs or sustained oscillations without clear external forcing, defying conservation expectations, sparking debates about measurement artifacts versus new physics. Ocean engineering intersects with these mysteries, as complex interactions among waves, currents, and sediments produce unpredictable erosion patterns and wave formations. Rogue waves, massive, sudden ocean waves, have been historically considered myths but now validated by satellite and shipborne measurements. Yet their formation mechanisms remain debated, blending nonlinear wave theory with chaotic dynamics. In micro and nanofluidics, surface tension and molecular layering create non-classical flow behaviors, challenging continuum assumptions of fluid mechanics. Slip flow, electric double-layer effects, and quantum fluid anomalies pose unresolved questions impacting lab-on-chip devices, biomedical sensors, and advanced cooling systems. Experimental limitations compound the mystery. High-fidelity measurements of fast, multi-scale turbulent phenomena demand exquisite instrumentation, while computational resources fall short in simulating realistic engineering scale flows. Fully resolving all relevant scales. Addressing these fluid and energy enigmas demands multidisciplinary approaches, combining theoretical physics, computational mathematics, experimental innovations, and applied engineering. Success promises breakthroughs transforming energy efficiency, environmental control, aerospace safety, and beyond, highlighting the vast frontier where known science meets the unknown. Within the vast universe of engineering materials and manufacturing, a host of perplexing anomalies persist that defy conventional scientific understanding, challenging engineers to rethink assumptions, innovate new theories, and refine practices. Material science, though grounded in physics and chemistry, reveals behaviors and transformations that routinely escape predictive control, while manufacturing processes occasionally produce results that defy explanation, threatening reliability and catalyzing breakthroughs. One prominent mystery arises in the unexpected aging and degradation of materials under seemingly stable environmental conditions. Metals, polymers, and composites degrade at rates that sometimes accelerate or slow without apparent cause, deviating from well-established corrosion, fatigue, and creep models. For example, certain steel alloys exposed to nominal stresses and temperatures demonstrate sudden brittle fracture after prolonged service, unexplainable solely by microstructural fatigue or stress corrosion cracking. Such anomalies hint at hidden microstructural transformations, including dislocation dynamics, impurity segregation, and phase changes, occurring at scales and timescales difficult to detect with standard techniques. Unraveling these subtle processes requires emergent in situ microscopy and advanced spectroscopy coupled with computational materials science. Yet many unexplained failures persist, jeopardizing critical infrastructure. Unexpected phenomena also arise in composite material behavior, highly valued for tailored strength-to-weight ratios, but notorious for complex failure modes. Delamination, matrix cracking, and fiber matrix interface failures sometimes initiate mysteriously amid seemingly uniform loading, interlaminar stresses, and manufacturing-induced defects interact in nonlinear, poorly understood ways, leading to unexpected fracture propagation. The anisotropic and heterogeneous nature of composites complicates predictive models, making their performance a domain of ongoing mystery and innovation. Developing sensor-embedded smart composites aims to detect early damage, yet the fundamental triggers for some failure modes remain elusive. In the domain of nanostructured materials, size effects and quantum phenomena introduce further unknowns. Materials at atomic and molecular scales exhibit electrical, mechanical, and thermal properties dramatically different from bulk counterparts. Phenomena such as enhanced strength in nanowires, unexpected conductivity shifts in graphene derivatives, or anomalous thermal transport in nanotubes challenge existing theory. The behavior of interfaces, grain boundaries, and defects at these scales introduces complexity that can cause abrupt property changes with minor compositional or environmental variations, defying reproducible manufacturing and usage predictions. Turning to manufacturing, additive manufacturing, AM, or 3D printing has revolutionized concept-to-part paradigms, but also produced baffling artifacts unexpected in traditional fabrication. Residual stresses, microcracks, porosity, and anisotropic mechanical properties arise unpredictably depending on scanning strategies, laser power, powders, and cooling rates. Even with sophisticated monitoring, understanding how these microstructural anomalies form and evolve during rapid melting and solidification challenges current metallurgical and thermal models. Strain localization and unexpected deformation modes detected in AM-produced parts provoke ongoing investigation and continuous technology refinement. Similarly, in casting and welding, unexpected defects, such as hot tears, shrinkage porosity, and cracking, sometimes appear even under controlled conditions. The fluid dynamics of molten metal flow, solidification kinetics, and thermal contraction interact in highly nonlinear fashions, complicating process control. Phenomena like macrosegregation, spontaneous grain refinement, or grain boundary embrittlement arise variably according to subtle compositional fluctuations or cooling rate histories, defying deterministic predictions, raising both practical and theoretical challenges. Manufacturing processes involving ceramics and glasses present mysteries involving nucleation and growth dynamics during sintering and cooling. Small variations in temperature profiles or atmosphere composition can induce sudden phase transformations or crystallization, leading to catastrophic brittleness or opacity changes that resist thorough mechanistic explanation. Controlling these effects is paramount in electronics, optics, aerospace, and biomedical applications. Furthermore, the phenomenon of triboluminescence, light emission when materials are fractured or rubbed, remains incompletely understood despite its intriguing quantum and mechanical facets. This effect, seen in minerals and engineered polymers, suggests unknown energy conversion pathways intertwining mechanical stress and electronic excitation within solid-state matrices. Superconductivity in certain alloys and compounds below critical temperatures, where electrical resistance disappears entirely, also defies total classical explanation. The microscopic nature of Cooper pair formation and the behavior of high-temperature superconductors represent ongoing mysteries with enormous engineering implications for power transmission and medical imaging. Micromechanical phenomena like strain localization and shear banding during plastic deformation in metals and polymers also challenge predictive models. These instabilities cause abrupt, localized failure, undermining component integrity in unexpected ways despite uniform macroscopic loading conditions. Scientists employ advanced tools, synchrotron radiation, electron tomography, atom probe microscopy, and in situ mechanical testing at nanoscale, seeking to visualize and quantify these subtle dynamic processes. Coupled multi-scale modeling, spanning atomic to continuum regimes, strives to bridge knowledge gaps. In manufacturing, Industry 4.0 initiatives leverage real-time sensor integration, machine learning analysis, and digital twins simulating process physics to detect, predict, and mitigate these unexplained phenomena, enhancing reliability and reducing waste. Yet, despite technological advances, mysteries persist because engineered materials and processes remain complex, multifactorial systems sensitive to environmental fluctuations, microscopic defects, and emergent phenomena challenging linear, deterministic models. Understanding and solving these material and manufacturing mysteries are vital. They underpin the safety, durability, and performance of everything from aircraft to medical implants, renewable energy components to infrastructure, ultimately shaping engineering's future horizons. As engineering has evolved from the mechanical to the digital age, the mysteries entrenched within electronics, control systems, and computational technologies have grown ever more intricate and profound. This realm, where the macroscopic world meets the quantum, and where real-world unpredictability challenges the deterministic logic of machines, presents some of the most baffling puzzles confronting engineers today. Part 5 plunges into the unexplained phenomena, anomalies, and paradoxes of modern electronics and control architectures, a fusion that underpins everything from smartphones and satellites to autonomous vehicles and industrial automation. Starting with electronics, we enter the domain where electrons, subatomic particles governed by quantum mechanics, assemble into devices expected to behave reliably under stringent design rules. yet sometimes refuse to comply. One baffling enigma is the random telegraph noise, RTN, observed in semiconductor devices. RTN manifests as sudden, discrete fluctuations in current or voltage within microelectronic components, sometimes large enough to degrade performance notably. Despite decades of study, the exact microscopic mechanisms remain partially unresolved. Theories involving charge trapping at defect sites, surface states, and atomic scale rearrangements provide partial explanations. Yet the stochastic nature and variability defy full deterministic modeling. In nanometer scale transistors powering modern microprocessors, RTN becomes a critical reliability issue, with unpredictable system-level effects. Quantum tunneling, once a purely theoretical construct, has practical consequences and mysteries within electronics. Electrons sometimes penetrate seemingly insurmountable energy barriers, leading to leakage currents in ultra-thin gate oxides and tunnel junctions. While tunneling is well understood qualitatively, the exact probabilities, coherence effects, and impact of materials' imperfections in complex device geometries introduce uncertainties impacting power consumption and device reliability in ways engineers continually strive to characterize and mitigate. Another challenge lies within electromagnetic interference, MI, and unexpected crosstalk in densely packed circuits. Noise coupling sometimes produces signal corruption at levels seemingly incompatible with classical shielding or isolation models. Temporal and spatial randomness of interference sources, coupled with nonlinear device responses, create emergent behaviors requiring novel materials, topology-aware circuit design, and adaptive filtering techniques. The full complexity of real-world electromagnetic environments makes absolute insulation elusive, as new wireless communication systems add unpredictable background noise levels. Turning to control systems, the establishment of complete control over complex, nonlinear, and uncertain systems remains elusive, although proportional integral derivative, PID control, and classical linear methods dominate. Many engineered systems present dynamics that deviate sharply from linearity. Unintended oscillations, chaotic responses, or bifurcations arise unexpectedly, defying conventional stability analyses and sometimes causing catastrophic failures in aerospace, power grids, and chemical plants. Adaptive and predictive control algorithms hold promise, but frequently experience model mismatch problems, where the real system behavior diverges from mathematical representations. This deviation results in performance degradation or instability not predicted by theoretical models, highlighting the inherent complexity of real-world processes embedding unknown disturbances, delays, and nonlinear couplings. Digital control systems, despite their accuracy, occasionally manifest unexpected behaviors like limit cycles, quantization noise effects, and clock jitter-induced errors, introducing anomalies in otherwise stable control loops. These discrete time-induced instabilities require sophisticated sampling theory application and often unforeseen engineering mitigations. The growing integration of artificial intelligence within control and decision systems opens another frontier of mystery and debate. AI algorithms, particularly those employing deep learning, operate as black boxes, making decisions through opaque, highly nonlinear computations. Trusting these systems in safety-critical domains is a major engineering challenge compounded by unpredictable failure modes emerging from adversarial inputs, data distribution shifts, or algorithmic biases. Understanding, predicting, and certifying AI system behavior remains an open problem with few rigorously accepted solutions. In computation, the phenomenon of hardware faults induced by cosmic rays and radiation poses a surprising puzzle. Single event upsets, where energetic particles flip bits or corrupt microprocessor states, can initiate random errors in memory and logic, even under normal operating environments. These soft errors, randomness, and distribution are difficult to predict, posing reliability challenges particularly in aerospace, defense, and data centers. Mitigation strategies, like error correction and radiation-hardened design, confront limits against ever-shrinking transistor scales. Another strange observation is the generation of electromagnetic pulses, EMPs, during switching in power electronics and integrated circuits. These pulses occasionally induce transient faults or disturb adjacent systems, unpredictably despite adherence to design guidelines, begging deeper understanding of interaction mechanisms between switching dynamics, parasitic inductances, and electromagnetic propagation. In the realm of quantum computation and information, although still largely theoretical and experimental, engineers face mysteries in maintaining coherence and mitigating decoherence, where fragile quantum states collapse unpredictably due to environmental interactions. Understanding how to stabilize and scale quantum systems while overcoming noise remains a monumental, unresolved engineering challenge, holding profound implications for future computational power. The burgeoning domain of Internet of Things, IoT, presents mysteries as myriad low-power devices interact wirelessly, often exhibiting unexpected interference, data packet loss, and security vulnerabilities. Emergent network behaviors arise as hundreds to thousands of devices concurrently communicate, creating congestion, latency, and synchronization issues notoriously difficult to model and resolve in heterogeneous environments. These unexplained behaviors in electronics and control systems underscore the delicate interplay between physical laws, device architectures, environmental factors, and complex system integration. They serve as catalysts for advancing device physics, control theory, signal processing, and cybersecurity. Engineers confront these mysteries by combining advanced experimentation, like ultra-fast spectroscopy and nanoscale imaging, with high-fidelity simulations, harnessing exascale computing, alongside innovative mathematical tools, integrating stochastic and chaos theories. Multidisciplinary collaborations, spanning physics, computer science, and material science, aim to unmask the hidden layers contributing to these enigmatic phenomena. Mastery of these engineering mysteries is crucial, as society's increasing reliance on electronics and automated control systems demands unprecedented robustness, reliability, and understanding to prevent failures and harness novel capabilities. Transportation engineering and mobility systems compose a vast, intricate tapestry weaving together infrastructure, vehicles, network dynamics, and human behavior to enable the movement of billions daily. Yet behind the veneer of smooth traffic flow and reliable transit, this complex ecosystem harbors puzzles and paradoxes that continue to elude complete explanation. This section embarks on an expansive journey into these transportation enigmas, phenomena defying classical engineering models and challenging planners, engineers, and scientists to rethink the fundamentals of mobility and infrastructure design. One of the earliest and most enduring enigmas in transportation is the phenomenon of traffic flow instabilities and phantom jams. Under certain traffic densities, flow spontaneously transitions from smooth to stop-and-go waves, without an obvious cause such as accidents or lane closures. This emergent behavior arises from complex human driving reactions, exhibiting nonlinearity, delayed responses, and anticipatory behaviors interacting unpredictably. Classical traffic engineering models based on steady-state assumptions cannot fully capture these self-organizing jams, which propagate backward, disrupting flow and increasing accident risks. Researchers investigate these phenomena using cellular automata, fluid dynamic analogies, and microscopic car-following models. Yet a universal predictive theory remains elusive, complicating congestion management. The design of urban intersections and signal timing also presents puzzles. Despite using adaptive control algorithms and traffic sensing technologies, some intersections demonstrate paradoxical behavior, where adding lanes or adjusting timing sometimes worsens congestion or increases accidents, a phenomenon known as Breis's paradox. Counterintuitive network effects challenge straightforward capacity expansion assumptions, revealing the intricacies of route choice, driver psychology, and network equilibrium states only partially captured by current transportation models. Such paradoxes inspire alternative approaches emphasizing demand management, multimodal integration, and network topology optimization over traditional capacity-centric planning. Infrastructure itself occasionally exhibits unexplained deterioration patterns. Pavement fatigue and cracking sometimes appear in highly variable spatial and temporal distributions, uncorrelated with traffic volume or material properties. Localized stresses, moisture intrusion, thermal cycling, and chemical reactions interplay in ways not fully understood, reducing life cycle predictions accuracy and maintenance effectiveness. Bridge expansions, joints, and bearings sometimes show anomalous wear, linked to undiscovered vibration modes or microclimates, prompting ongoing structural health monitoring research employing sensor networks and AI analytics. Rail systems reveal their own mysteries. While track geometry and material behavior are studied rigorously, certain vibrations termed rail corrugation or wheel squeal manifest unexpectedly due to complex wheel-rail interactions involving high-frequency elastic waves and frictional dynamics. These issues lead to noise pollution, accelerated maintenance needs, and operational limitations. Yet precise causal modeling resists full formulation, prompting continuous empirical investigation. Aviation, an engineering marvel, encounters atmospheric unpredictability, causing what is colloquially known as clear air turbulence. Invisible, unforeseen air disturbances, creating violent aircraft jolts without associated weather phenomena. Detectable by radar, the precise genesis involves complex airflow patterns, jet streams, and atmospheric gravity waves poorly predicted by weather models, posing operational hazards, challenging pilot responses, and aircraft design. Emerging autonomous vehicle technologies open a new frontier riddled with uncharted challenges. Beyond sensor reliability and algorithmic accuracy, autonomous systems exhibit unexpected failures when encountering rare or ambiguous situations, decision paradoxes when multiple goals conflict, and unpredictable human-autonomous vehicle interaction dynamics. Understanding these failure modes requires synthesizing behavioral engineering, AI robustness theory, and traffic flow interactions, frontiers still being actively charted. The emergent phenomenon of mobility as a service (MaaS), integrating multimodal transport through digital platforms, presents systemic mysteries surrounding user behavior, demand elasticity, and network resilience. The dynamics of shared mobility, ride-hailing fleet management, and micro-mobility adoption generate fluctuating demand patterns and infrastructure stresses defying traditional forecasting, calling for novel analytic models blending economics, sociology, and complex systems theory. Environmental interactions complicate transportation enigmas further. Urban heat islands affect pavement materials and traffic flow. Noise propagation and air quality dispersion reveal complex wave and chemical transport behavior, sensitive to micro-scale geometric details. Climate change introduces long-term uncertainties, with extreme weather affecting infrastructure integrity and operation demanding adaptive engineering responses. Data-rich intelligent transportation systems. ETS seek to alleviate some mysteries by real-time sensing, predictive analytics, and adaptive controls. Yet integration, standardization, privacy, and cybersecurity concerns limit widespread implementation, leaving qualitative insights and anecdotal experience often dominating decision processes. Cutting-edge research embraces agent-based simulations, modeling individual vehicle and pedestrian behaviors, fostering emergent traffic dynamics, insights, novel sensor deployments, such as LiDAR-equipped drones and crowdsourced smartphone data, offer unprecedented spatiotemporal resolution informing system optimization. This part underscores that transportation engineering mysteries extend beyond physical infrastructure into human-machine interactions, complex network effects, and emergent behaviors defying reductionist models. They emphasize the need for holistic, interdisciplinary approaches combining engineering, computer science, social sciences, and environmental studies. Bridging these mysteries fosters resilient, efficient, and equitable mobility systems vital for economic vitality and quality of life in burgeoning urban and interurban landscapes. In the vast theater of engineering, where monumental structures and machines endure relentless forces over time, the domain of structural dynamics, fatigue, and failure prediction emerges with profound mysteries. Despite rigorous scientific foundations and advanced monitoring technologies, the behavior of materials and assemblies under cyclic loading and fluctuating environments continues to defy full understanding, occasionally culminating in catastrophic and unexpected failures. This part dives deeply into the enigmatic complexities that persist at the heart of ensuring the safety, reliability, and durability of engineered systems. Structural fatigue, a progressive, localized damage mechanism occurring under repetitive stress cycles, has been studied extensively for decades. Yet prediction remains notoriously imprecise. Traditional models commonly base life estimates on empirical SN stress life curves, derived from laboratory specimens tested under idealized cyclic loadings. Yet real-world conditions impose variable amplitude loading, multi-axial stresses, environmental exposure, and residual stresses that complexify material response. Components sometimes fail significantly earlier or survive longer than predicted. These discrepancies highlight unresolved interactions between microstructural damage accumulation, crack initiation mechanisms, and crack propagation dynamics under complex service conditions. At the micro scale, fatigue initiation involves intricate phenomena such as persistent slip bands, localized plasticity, strain-induced grain boundary migration, and micro-void nucleation. These processes can be influenced by impurities, phase distributions, and manufacturing-induced defects like inclusions or surface roughness. Such heterogeneities introduce spatial variability in material susceptibility, tremendously complicating crack nucleation prediction. Advanced in situ microscopy and synchrotron studies are beginning to unravel these processes, but a comprehensive predictive framework bridging atomic scale mechanisms to macro scale fatigue remains elusive. Crack propagation introduces further challenges. While fracture mechanics provides tools to relate stress intensity factors to crack growth rates, unexpected accelerations or retardations of propagation under variable loading or corrosive environments often appear. Environmental assisted cracking, EAC, hydrogen embrittlement, and fretting fatigue phenomena demonstrate synergistic interactions between mechanical, chemical, and electrochemical factors difficult to quantify comprehensively. Under certain conditions, microstructural transformations triggered by cyclic stress accelerate crack growth beyond all conventional predictions, producing mysterious early failures in critical components such as aircraft wing spars, nuclear reactor pressure vessels, and offshore platform support structures. High-frequency vibrations and dynamic loading scenarios introduce further enigmas. Structures subjected to impact, seismic, or blast loads exhibit markedly complex, nonlinear responses, including localized plasticity, dynamic strain aging, and rate-dependent failure modes, seldom captured fully by models derived from static or low-rate tests. The transition from ductile to brittle behavior under dynamic conditions is not fully characterized for modern materials, posing safety concerns across transportation, defense, and civil infrastructure. Creep fatigue interactions in high-temperature environments represent another domain of ongoing uncertainty. Components in power plants and aero engines exposed to sustained elevated temperatures alongside mechanical cycling display degradation modes, difficult to separate and quantify distinctly. Microstructural coarsening, oxidation and internal stress evolution interplay, unpredictably altering damage evolution paths. Current design codes rely on conservative bounds, often leading to premature replacements, but do not capture the nuanced physics dictating actual material behavior. Monitoring techniques, critical for early damage detection, face their own puzzles: acoustic emission sensors, strain gauges, and ultrasonic inspections sometimes detect precursor signals whose correlation with imminent failure remains ambiguous, distinguishing benign microstructural noise from critical damage progression challenges. Signal processing and interpretation. False positives inflate maintenance costs, while false negatives risk catastrophic loss. Prognostics and health management PHM systems, leveraging machine learning on sensor data, seek to predict remaining useful life, but variability in operational conditions and limited failure datasets hinder reliable generalization. Data-driven approaches often confront the black box dilemma, limiting interpretability and trust in predictions. Sensor technologies themselves encounter surprises. Piezoelectric sensors degrade unpredictably under fatigue, while embedded fiber optics witness unexpected signal drift, complicating strain measurements within composites. Materials with complex architectures, like fiber-reinforced polymers and additive manufactured components, reveal fatigue behaviors non-intuitive relative to traditional metals, including progressive delamination and porosity growth attributed failure modes not accounted for in legacy models. Environmental factors such as corrosion, thermal cycling, and radiation exposure spawn synergistic damage mechanisms, accelerating fatigue beyond isolated effect. Extrapolations, posing challenges in offshore, nuclear, aerospace, and infrastructure applications. Human factors contribute mystery further. Maintenance practices, inspection intervals, and operational profiles introduce variability difficult to model accurately, yet critical to structural longevity. Emerging in this field are integrated multi-scale models, combining crystal plasticity, finite element fracture simulation, and probabilistic risk assessments, striving to encapsulate complex failure processes. High-performance computation, coupled with experimental validation, attempts to close gaps, but formidable obstacles remain. Interdisciplinary collaboration among material scientists, structural engineers, chemists, and data analysts is vital to unravel layered mysteries extending from atomistic degradation events to full-scale structural system failures. Capturing and demystifying these phenomena are not mere academic pursuits but necessities. Failure to understand fatigue accurately risks lives, environmental catastrophes, and economic fallout. This chapter serves as an exploration into the labyrinth of fatigue and failure mysteries, inviting engineering to push boundaries in theory, experimentation, and monitoring technology to build safer, longer-lasting structures for future generations. Robotics and artificial intelligence. AI represent one of the most dynamic frontiers of modern engineering, where the intersection of mechanical systems, digital cognition, and autonomous control constructs machines that challenge our very notions of capability and predictability. Despite remarkable progress and widespread deployment, this transformative domain harbors profound mysteries and unpredictable behaviors that continue to elude definitive engineering explanation, creating a fertile ground where innovation coexists with puzzling anomalies. At the core lies the challenge of robust autonomy, endeavoring to create robots capable of operating safely and effectively in complex, unstructured, and dynamic environments, without human intervention. While classical control theory governs mechanical stability and feedback regulation, real-world deployment exposes systems to unforeseen variables, ambiguous sensory input, and dynamic interactions, producing emergent behaviors difficult to predict or model accurately. For instance, autonomous vehicles navigating urban settings must interpret partial, noisy, or contradictory sensor data, handle unpredictable human actors, and make split-second ethical decisions, a cocktail of complexity still far from fully understood or mastered. The cognitive layer introducing machine learning and deep neural networks brings additional layers of opacity and non-linearity. AI algorithms, although powerful in pattern recognition, often behave as a black box, offering limited interpretability regarding their decision processes. This opacity raises challenges in safety-critical applications, where understanding the rationale for an autonomous decision is paramount. Engineers face difficulties explaining and predicting failure modes arising from subtle data biases, adversarial inputs, or scenario extrapolations unseen during training. This unpredictability manifests in phenomena like overfitting, model collapse, or unexpected behavior shifts, complicating certification, trust, and deployment. Robotic manipulators confront mechanical and control puzzles, particularly in force feedback and dexterity, where replicating human-like tactile sensing and manipulation within complicated tasks remains elusive. The integration of distributed sensing, compliant mechanisms, and real-time adaptive control is a work in progress, with some unexplainable transient instability or unintended oscillations observed during high-precision tasks, posing reliability concerns. Multi-robot systems and swarm robotics, inspired by natural collective behaviors such as ant colonies and bird flocking, introduce mysteries in decentralized coordination and emergent group intelligence. Self-organization protocols produce robust, scalable solutions, yet also manifest unpredictable synchronization, phase locking, or fragmentation patterns unanticipated by design, raising fundamental questions about the limits of decentralized control and information flow. Human-robot interaction, HRI, amplifies these enigmas, where robots interpret and predict human intentions and emotions through complex multimodal data, such as speech, gesture, and physiological signals. Generating timely, socially acceptable robotic responses in noisy, culturally diverse contexts remains an active challenge. Unexpected behaviors such as misinterpreted gestures or emotional mismatches highlight limitations in current modeling of human cognition and social signaling, requiring advances in neuroengineering, psychology, and AI ethics. Soft robotics introduces unique material science mysteries, engineered from compliant, flexible, and sometimes bio-inspired materials. Soft robots exhibit novel deformation modes and locomotion strategies, but also unpredictable hysteresis, creep, and fatigue, complicating precise control. Their constitutive modeling at the continuum and molecular scale remains an evolving field as engineers endeavor to predict performance under complex loading and environmental conditions. Robot learning from demonstration, imitation learning, and reinforcement learning have transformed autonomy, but also introduce mysteries concerning transferability and generalization. Robots trained in controlled laboratory environments sometimes fail unpredictably in novel real-world scenarios due to subtle discrepancies known as the reality gap. Understanding and bridging this gap involves unraveling complex interplay between perception, motor control, and environment dynamics currently only approximated through heuristic or empirical methods. Energy management in mobile and humanoid robots reveals another labyrinth. Battery life, power density, and thermal dissipation must be balanced within tight size and weight constraints. Some robotic swarms utilize wireless energy transfer, producing complex electromagnetic interference patterns, not fully predictable, affecting both robustness and human safety. In collaborative industrial robotics, integration and control of multiple heterogeneous robotic agents present unresolved challenges in conflict resolution, resource allocation, and fault tolerance, especially in unstructured, dynamic shop floor environments. Unanticipated emergent behaviors such as deadlocks, oscillations, or synchronization failures underscore gaps in system-level engineering frameworks. Cybersecurity presents a critical and evolving mystery. Autonomous and networked robotic systems are vulnerable to hacks, spoofing, and data manipulation. Securing communication, control, and data integrity under real-time constraints remains a demanding area where theoretical solutions are often difficult to implement fully without introducing new vulnerabilities. Quantum computing and neuromorphic hardware herald futuristic computational paradigms for robot intelligence. Yet their engineering principles and emergent behaviors challenge classical design and debugging methodologies nearly incomprehensible within current frameworks. Researchers employ comprehensive heterogeneous sensor suites, high-fidelity physics simulations, and AI explainability techniques, striving to demystify robot behaviors and spur safer, more intelligent machines. Nonetheless, the coalescence of real-time physical dynamics, high-dimensional perception, and adaptive learning ensures many mysteries persist. The implications are profound. As robots and AI systems permeate healthcare, defense, manufacturing, and daily life, confronting their mysteries is essential to unlocking transformative potential while safeguarding humanity. In the intersection of energy infrastructure and environmental engineering lies a landscape of engineering mysteries that strain current knowledge and threaten to derail the stability and sustainability of critical systems. Humanity's grand quest for sustainable development and environmental stewardship is challenged profoundly by phenomena in these domains that resist complete scientific characterization, posing unresolved questions with far-reaching practical consequences. This segment embarks on an exhaustive investigation into these perplexing enigmas. Beginning with electrical power grids, the technological marvels enabling society's energy pulse, we confront the elusive challenge of grid stability and blackouts. Despite advanced control systems, unforeseen cascading failures occasionally plunge vast regions into darkness. The causes involve complex nonlinear dynamics where seemingly minor disturbances propagate through interdependent networks, triggering overloads, protective relay misoperations, and voltage collapses. Traditional power flow models assume quasi-static conditions and linear behavior, yet real-world grids exhibit nonlinear oscillations and instability modes under contingencies, renewable integration variability, and fluctuating loads. Rising penetration of intermittent renewables exacerbates unpredictability, with grid inertia reduction impairing frequency regulation. Emerging concepts such as chaos theory, complex network analysis, and machine learning-based early warning systems aim to unravel these mysteries, but comprehensive predictive models remain incomplete. In transmission lines and substations, unexpected dielectric failures and corona discharge patterns defy classical electrostatics predictions. Localized ionization phenomena and airborne particulate interactions produce stochastic degradation accelerating insulator aging. Subtle variations in pollutants, humidity, and electric field geometries manifest in unpredictable flashovers or contamination-induced currents, revealing knowledge gaps in surface physics and plasma interactions under environmental conditions. Energy storage systems, pivotal for smoothing supply-demand imbalances, present deep enigmas. Lithium-ion battery degradation, discussed earlier, intertwines with grid-scale storage technologies where mechanisms of capacity fade and thermal runaway display, pronounced stochasticity and environmental sensitivity beyond current understanding. Flow batteries, compressed air energy storage, and thermal molten salt systems encounter unexpected material compatibility issues, operational inefficiencies, and energy losses traceable only partially through current thermodynamic or electrochemical models. In environmental engineering, water treatment and distribution infrastructures often reveal anomalous contamination or biofouling patterns unexplained by modeled hydraulic and chemical parameters. Microbial communities exhibit dynamic behaviors including sudden blooms or die-offs altering water quality unpredictably. Membrane filtration technologies face unexplained flux declines and poor-scale fouling modes resisting general predictive frameworks. Understanding biofilm formation, chemical cross-interactions, and microparticle aggregation at nanoscale remains a frontier challenge with direct implications for public health and resource management. Similarly, wastewater treatment plants experience variable organic and nutrient removal efficiencies. Biological process models, although robust, sometimes fail to predict sudden operational upsets rooted in complex microbial ecology. Interactions poorly understood at macro and micro scales. Fluctuations in influent composition and environmental factors induce nonlinear responses not fully captured, causing design margins to be conservative, yet insufficient in some cases. Waste management systems report anomalies in landfill gas generation and leachate composition, with temporal variations beyond expected decay dynamics. These compositional and flux changes complicate methane capture strategies and contamination risk assessments, demanding enhanced geochemical and microbial understanding. Waste-to-energy systems, while promising sustainable solutions, encounter unexplained transient combustion instabilities, emission spikes, and residue formation that process models incompletely predict, complicating control and compliance. On a broader scale, climate-resilient infrastructure design confronts uncertainties assessing future environmental loads. Sea level rise, intensified storms, temperature fluctuations, and shifting precipitation patterns introduce variable stresses and degradation pathways, inadequately characterized by historical data-driven models. The multi-factor, multi-scale coupling of climate processes with asset lifespan and performance introduces profound uncertainty into engineering decision frameworks. Carbon capture and storage, CCS, and geoengineering techniques designed to mitigate climate change raise technical enigmas, including deep subsurface CO2 migration pathways, leakage potentials, mineralization rates, and ecological impacts. The coupled hydromechanical chemical processes governing long-term storage stability are complex with incomplete experimental data. Urban infrastructure systems face urban heat island effects, creating localized thermal anomalies affecting building energy loads, material aging, and human comfort. The interactions of urban geometry, material albedo, vegetation, and anthropogenic heat emissions defy simple characterization, necessitating novel integrative modeling approaches. Environmental pollution, transport, and dispersion entail complex dynamics where pollutants traverse soil, air, and water pathways, influenced by heterogeneous media properties and stochastic atmospheric variations. Predictive modeling remains challenged by these multi-phase, reactive transport phenomena, introducing uncertainties in risk assessment and remediation design, electric and hybrid vehicle charging networks, integral to energy transitions, manifest unexpected load patterns impacting grid stability, user behavior, charging power variations, and vehicle-to-grid interactions produce complex demand profiles resisting straightforward forecasting, complicating infrastructure investment and operation. In waste heat recovery applications across industrial sectors, anomalous thermodynamic inefficiencies are observed, where thermal gradients and phase change processes exhibit unexpected interactions possibly linked to material microstructure and flow turbulence. Coupling advances in sensing, data analytics, real-time monitoring, and digital twins aim to confront these enigmas. However, the heterogeneity, multi-scale nature, and evolving environmental contexts of these systems require continuous interdisciplinary collaboration and innovation. Understanding the mysteries embedded within energy infrastructure and environmental engineering not only advances scientific knowledge, but safeguards global economic, ecological, and human well-being amidst rapid technological evolution and environmental change. Transportation systems epitomize the intricate confluence of infrastructure, vehicles, human behavior, and technology, sustaining the mobility needed for contemporary societal function. Yet beneath the facade of ordered movement, elegant engineering, and efficient logistics exist profound enigmas that unsettle the predictive capabilities of existing models and challenge the engineering community to unravel fundamental questions. This part embarks on an in-depth, expansive examination of the confounding mysteries underpinning transportation networks, vehicle dynamics, and human-machine interaction shaping the future of mobility. One of the foremost puzzles in transportation is the spontaneous emergence of phantom traffic jams, waves of congestion materializing without apparent cause or physical obstruction. These phenomena arise due to nonlinear interactions among drivers, vehicular accelerations and decelerations, reaction time delays, and roadway conditions. Such emergent stop-and-go patterns propagate backward against traffic flow and significantly reduce throughput and increase accident probability. Although mathematical models like cellular automata and fluid dynamic analogies offer descriptive insight, accurately predicting formation onset, wave amplitude, and dissipation remains elusive, compromising traffic management strategies. Equally mystifying is Brace's paradox, wherein adding roadway capacity paradoxically worsens overall traffic performance, reversing the intuitive cost-benefit assumption. This counterintuitive network effect emerges from individual driver route choice behaviors that optimize personal travel time but degrade collective system efficiency, leading to increased congestion and emissions. Network topology, demand elasticity, and behavioral idiosyncrasies combine nonlinearly, producing equilibria challenging to characterize analytically. Current transportation engineering grapples with integrating these game-theoretic concepts into practical infrastructure design and policy frameworks. Infrastructure deterioration presents further mysteries. Pavement fatigue and distress do not always correlate simply with traffic load or environmental exposure. Variations in subgrade composition, moisture infiltration, freeze-thaw cycles, and chemical interactions influence longevity in unexpected ways. Similarly, bridge expansion joints and structural bearings exhibit unanticipated wear and noise phenomena possibly linked to microclimatic variabilities and intricate load interactions, poorly captured by standard fatigue analysis. Railway infrastructure and rolling stock exhibit difficult to predict phenomena as well. The onset of rail corrugation, characterized by quasi-periodic rail surface patterning, leads to elevated vibration levels, noise emissions, and increased maintenance costs. This wear pattern, emerging from wheel-rail contact dynamics, frictional instabilities, and material responses, resists comprehensive theoretical modeling. Similarly, wheel squeal, high-frequency acoustic noise arising in tight curves, arises from complex frictional stick-slip cycles with sensitivities to material properties, lubrication, and track geometry posing persistent engineering challenges. The aviation sector contends with clear air turbulence, AATTA, erratic, invisible atmospheric disturbances that abruptly jolt aircraft without warning from conventional meteorological instruments. The underlying fluid dynamics involve intricate interactions between jet streams, gravity waves, and thermal stratification, yet prediction remains probabilistic at best. TAAT poses risk to passenger safety and operational efficiency, driving research into enhanced sensing and atmospheric modeling. Emerging autonomous vehicle ecosystems layer new complexities atop classical transportation mysteries. Sensor fusion, decision-making under uncertainty, and ethics in critical scenarios pose challenges in designing systems that can handle rare, ambiguous, or conflicting inputs reliably. Autonomous fleets interacting with human drivers and pedestrians generate emergent traffic patterns incompletely understood, provoking new questions about control, safety, and system optimization. Shared mobility and micromobility modes spurred by digital platforms introduce unpredictable demand patterns and spatial temporal fluctuations. These trends frustrate conventional network planning and resource allocation models, requiring integration of behavioral economics, real-time analytics, and adaptive infrastructure design. Environmental dynamics further complicate matters. Urban heat islands induce localized thermal stresses, affecting pavement surfaces and mobility equipment. Noise and air pollution transport depend on intricate multipath wave propagation and turbulent dispersion influenced by complex urban geometries, challenging mitigation strategies. Transportation infrastructures increasingly embrace digitalization via intelligent transportation systems, ITS, employing sensor arrays, communication networks, and data analytics to enable real-time monitoring, adaptive control, and predictive maintenance. Yet, integration complexity, cybersecurity risks, and privacy concerns temper anticipated benefits, necessitating interdisciplinary approaches. Research harnesses agent-based modeling capturing individual vehicle and traveler behaviors, enabling granular insights into emergent macroscopic phenomena. High-resolution data from GPS, LiDAR, and crowdsourcing enrich models underpinning adaptive traffic signal control and incident detection. This exploration reveals transportation as a living, complex adaptive system with nonlinear interactions spanning physical infrastructure, vehicles, human agents, and environmental factors. The unresolved mysteries serve as catalysts for new theories, innovative technologies, and forward-looking policies aimed at crafting safer, more efficient, and sustainable mobility paradigms suited for rapidly evolving societal needs. Structural mechanics, fatigue, and failure prediction constitute the backbone of safe and durable engineered systems. These disciplines translate the fundamental principles of material behavior under stress into reliable lifetime assessments and proactive maintenance strategies. Yet within these well-established frameworks emerge persistent enigmas, unaccounted phenomena, and unexpected failure modes that confound engineers and demand ever deeper scientific inquiry. This part undertakes a comprehensive examination of these enduring mysteries, exposing the nuanced interplay of physics, material science, and practical engineering that governs structural resilience and failure. At the forefront of these mysteries is the unpredictable nature of fatigue, crack, initiation, and propagation. Fatigue failure, characterized by microcrack formation under cyclic stresses well below material yield strength, accounts for a significant proportion of structural collapses and equipment malfunctions. Traditional design methods rely on laboratory-derived empirical data and fracture mechanics concepts, which, while effective in standardized conditions, often fail to capture the full realities of operational environments. Real-life service involves complex variable amplitude loading regimes, multi-axial stress states, environmental corrosion, temperature fluctuations, and material heterogeneity. These factors produce fatigue lives, deviating widely from predictions, sometimes by orders of magnitude, posing formidable challenges in safety-critical industries such as aerospace, nuclear, automotive, and civil infrastructure. The microscopic processes driving crack initiation involve localized plastic deformation, persistent slip bands, and grain boundary weakening, among others. These mechanisms unfold heterogeneously within the material microstructure, influenced by manufacturing defects, impurity segregation, and residual stresses. Imaging techniques such as electron microscopy and X-ray tomography have begun to reveal these subtle damage precursors. Yet translating this insight into robust predictive models remains elusive, particularly as service conditions modulate damage evolution unpredictably. Crack growth kinetics further complicate life prediction. The propagation stage is influenced by stress intensity factors, but environmental factors such as moisture, corrosion, and temperature can accelerate or retard crack advance. Through mechanisms like stress corrosion cracking or hydrogen embrittlement. These synergistic effects introduce nonlinearities, defying existing fracture mechanics. Approximations, accelerated or delayed failures occur even when standard inspections indicate acceptable crack sizes or loads. Fatigue interactions with other degradation mechanisms, notably creep at elevated temperatures or fretting in mechanical joints, produce complex damage pathways. Creep fatigue coupling involves time-dependent plastic deformation and microstructural recovery or coarsening processes, creating damage accumulation patterns, poorly represented in current life assessment codes. Fretting, arising from micromotion at bearing surfaces or bolted joints, induces wear and crack nucleation, exacerbating fatigue loads beyond anticipated levels. Dynamic loading introduces additional complexities, forcing structural components into nonlinear response regimes seldom captured in static or quasi-static fatigue analyses. Impact, vibration, seismic excitation, and blast loading induce rapid energy transfers. Plastic deformation and damage accumulation involving phenomena such as strain rate sensitivity and dynamic strain aging still not fully quantified for engineering materials. Monitoring and prognostics technologies seek to uncover hidden fatigue damage progression through acoustic emission detection, ultrasonic inspection, strain and crack growth sensors, and other non-destructive evaluation methods. However, distinguishing meaningful precursor signals from noise or benign microstructural activity is challenging. Data interpretation remains muddied without comprehensive failure databases and high-fidelity models capable of correlating sensor outputs with imminent failure likelihood. Advanced modeling approaches aim to bridge scales from atomistic dislocation dynamics to continuum fracture propagation using crystal plasticity, phase field methods, and multi-scale simulations. These techniques offer promising pathways to resolve the intricate mechanisms of fatigue damage, yet require further validation and computational refinement before routine deployment. Structural health monitoring systems enhanced by machine learning incorporate vast sensor data streams to infer remaining useful life and forecast failures, yet model generalizability and uncertainty quantification remain concerns as new materials and complex load scenarios enter service environments. Composite materials, featuring layered heterogeneous architectures, introduce unique fatigue challenges. Interlaminar stresses, micro-cracking within matrix phases, fiber breakage, and delamination display damage evolution markedly different from conventional metals. nonlinear coupling among damage modes complicates measurement and prediction. Additive manufacturing reshapes fatigue considerations through rapid solidification microstructures, residual stress patterns, and anisotropic mechanical behavior, producing unexpected failure modes not yet fully described in design standards. Human factors, such as operational practices, maintenance intervals, and load variability, introduce stochastic elements further confounding predictive accuracy. Fundamentally, these mysteries underscore that material degradation and failure are emergent phenomena arising from an interplay of physics across scales and environments, challenging the sufficiency of deterministic models. Resolving these complex enigmas is essential to safeguarding critical structures and mechanical systems, reducing life cycle costs, and advancing engineering reliability and safety. This chapter frames structural fatigue and failure prediction as a deep interdisciplinary enigma at the confluence of materials science, mechanics, monitoring technology, and data analytics pivotal to tomorrow's resilient engineering. At the frontier of engineering science lies the emerging domain of quantum and nanoengineering, a fascinating yet enigmatic realm where classical physics surrenders to quantum laws and the nanoscale reigns supreme. This domain promises revolutionary advancements in computation, materials, sensing, and energy, yet it is riddled with mysteries that challenge both understanding and application. This part explores the multifaceted enigmas shaping the next generation of engineering innovations, from quantum coherence conundrums to nanoscale fabrication paradoxes and emergent phenomena defying current paradigms. Quantum engineering harnesses the peculiar behaviors of quantum systems, superposition, entanglement, and tunneling, to construct devices and platforms, transcending classical limitations. However, sustaining quantum coherence, the delicate state necessary for quantum computation and sensing, remains one of the most profound mysteries and obstacles. Despite meticulous isolation techniques, quantum qubits succumb to decoherence induced by unavoidable environmental interactions, fluctuating electromagnetic fields, and material imperfections. The bewildering aspects include unexpected decoherence pathways, time-dependent noise characteristics, and material-dependent susceptibilities. The precise mechanisms governing these lost channels remain partly understood, mandating intense research into quantum error correction codes, material engineering, and novel qubit designs, such as topological qubits intended to intrinsically shield coherence. Another vexing phenomenon is the challenge of quantum measurement and collapse, where the act of observation seemingly freezes the quantum state into a definite outcome, yet without a fully unanimously accepted theoretical explanation. This measurement problem sits at the interface of physics and information engineering, influencing the design of quantum algorithms and systems by constraining how information can be reliably extracted without destroying the fragile quantum states. At the nanoscale, material behavior departs radically from bulk properties, introducing unexplained anomalies. Size-dependent phenomena manifest in electrical, optical, mechanical, and thermal properties. Nanoparticles exhibit altered melting points. Quantum dots show discrete electronic states, and nanowires display enhanced mechanical strength, surpassing macroscopic counterparts. However, the precise relationship between quantum confinement, surface effects, and defects generating these deviations is not completely characterized, complicating predictive materials design. Phenomena such as unexpected thermal conductivity deviations and anomalous electron mobility confound current theoretical models and challenge nanofabrication controls. Fabrication itself at such scales is fraught with mysteries. While lithographic and self-assembly techniques can create structures of atomic precision, stochastic defects, surface reconstructions, and unintentional contaminations cause properties variations that are not fully understood or controllable. Atomic scale rearrangements occurring spontaneously during processing or operation defy exact prediction, impacting device yield and functionality, emphasizing the need for real-time nanoscale characterization tools still under development. In quantum transport and nanoelectronics, electrons behave both as particles and waves, resulting in interference patterns and phenomenon like ballistic transport and Coulomb blockade. Yet, unexplained conductance fluctuations and noise persist even under highly controlled environments. Electron-phonon interactions and quantum decoherence at these scales exhibit complex dynamics influencing device performance unpredictably. Quantum materials such as topological insulators, Weyl semimetals, and superconductors harbor exotic states of matter showing remarkable robustness to disorder and magnetic fields. Yet the microscopic origins of their boundary states, spin-orbit couplings, and interplay with defects and temperature variations pose ongoing, unresolved questions intricately connecting condensed matter physics and materials engineering. Quantum sensing technologies exploit entanglement and superposition for unprecedented sensitivity, enabling nanoscale magnetic field mapping, gravimetry, and biological imaging. Yet challenges arise in generating, preserving, and reading out quantum-enhanced sensor states across practical environmental ranges, revealing gaps between laboratory success and field deployment. Quantum communication systems reveal fascinating mysteries concerning entanglement distribution over long distances, quantum repeaters, and network scalability, photon loss, decoherence, and secure key generation protocols offer rich areas of theoretical and experimental investigation as the race for practical quantum internet accelerates. In energy applications, nanomaterials exhibit unexpected photocatalytic and thermoelectric behaviors surpassing theoretical limits. The mechanisms often involving complex electron-hole interactions, surface plasmon effects, and quantum confinement remain partially elusive, limiting rational design of efficient solar fuels and waste heat harvesting technologies. Spintronics, leveraging electron spin rather than charge, opens pathways to low-power memory and logic devices, but struggles with understanding spin relaxation times and coherence in realistic material systems impeded by subtle scattering phenomena and interface effects. This realm also intersects with molecular machines, nanoscale entities mimicking biological motors, raising questions about energy transduction efficiencies, control mechanisms, and integration into larger systems currently at the experimental frontier. Experiments use ultra-fast spectroscopy, scanning tunneling microscopy, electron holography, and cryogenic technology to probe these mysteries, while computational physics employs density functional theory, quantum Monte Carlo, and hybrid quantum classical simulations seeking predictive power, though computational costs remain high. Ethical implications arise surrounding quantum information privacy, equitable access to revolutionary technologies, and security in an era of quantum computing potentially undermining classical cryptography. The path forward demands unprecedented collaboration across physics, material science, computer science, and engineering disciplines alongside innovative educational paradigms to cultivate a workforce capable of traversing this intricate landscape. In essence, quantum and nanoengineering represent an awe-inspiring and challenging frontier, where nature reveals hidden layers of order and complexity. The mysteries here do not just push the boundaries of engineering, but question the very fabric of reality, holding the keys to transformative technologies influencing computing, communication, energy, and medicine for decades to come. Biomedical engineering stands as a beacon of interdisciplinary convergence, where biology, medicine, mechanics, electronics, and information science meld to confront some of the most profound challenges of human health and longevity. However, beneath the visible triumphs of imaging, prosthetics, and diagnostics lie perplexing mysteries and unexplained phenomena that challenge the limits of scientific understanding and engineering ingenuity. This segment embarks on an exhaustive exploration of these biomedical enigmas, unmasking the complexities and frontiers that define the quest to decode, repair, and augment the human body. At the core of biomedical engineering is the challenge of tissue regeneration and repair. The intricate orchestration of biological and mechanical cues to heal or replace damaged tissues and organs. While stem cell therapies and biomimetic scaffolds promise revolutionary advances, mesoscopic and microscopic phenomena governing cell differentiation, migration, and extracellular matrix remodeling often diverge unpredictably from theoretical models. For instance, engineered scaffolds, designed to mimic native tissue stiffness and chemistry, sometimes provoke unforeseen cellular responses such as aberrant differentiation or immunogenic rejection. The exact mechanotransduction pathways, how mechanical forces translate to genetic activity and phenotypic modulation, remain incompletely characterized, impeding reliable clinical translation. The biomaterial host interface presents further mysteries. Despite advances in synthetic and natural biomaterials designed for biocompatibility, implants often encounter unanticipated immune reactions, fibrous encapsulation, or degradation unexpected from in vitro assays. The dynamic interplay of protein adsorption, cell adhesion, immunomodulation, and microenvironment evolution challenges engineers attempting to design inert yet integrative interfaces, especially for long-term implants such as cardiovascular stents or neural electrodes. Medical imaging, a field transforming diagnostics, also cloaks enigmas. For example, magnetic resonance imaging, MRI, exploits nuclear spin properties, modulated by magnetic fields, yet signal quantification and interpretation frequently involve ambiguous contrasts and artifacts, subtle tissue heterogeneities, or chemical exchange processes generate unexpected variations, complicating diagnosis. Novel contrasts relying on emerging techniques such as hyperpolarization reveal physiological processes, but introduce transient phenomena, difficult to capture reproducibly. Advanced imaging modalities uncover microstructural heterogeneity with unprecedented resolution, yet relating these observations quantitatively to functional outcomes or disease progression remains a sophisticated challenge at the intersection of biology, physics, and computation. Electrophysiology engineering exemplifies mystery in the nervous system interface. Neural prosthetics and brain-computer interfaces, BCIs, restore functions in paralyzed or amputated patients, but suffer from degraded signal quality over time. Poorly understood tissue-electrode interface electrochemistry, and baffling variability in decoding brain signals. The fundamental neurophysiological mechanisms governing signal propagation, synaptic plasticity, and network dynamics underpinning cognitive and motor functions elude comprehensive modeling, complicating development of efficient BCIs. Biomechanics, analyzing the mechanical behavior of tissues, organs, and whole organisms, confronts mysteries in material anisotropy, viscoelasticity, and active contraction mechanisms. Human tissues exhibit unique, nonlinear, time-dependent mechanical responses involving hierarchical microarchitecture and cellular activity, predicting injury thresholds, or optimizing rehabilitation devices requires models that integrate multi-scale mechanics with biological feedback loops, a formidable task where discrepancies between in vitro measurements and in vivo responses persist. Biomedical signal processing and health informatics aim at extracting clinically meaningful information from noisy, complex physiological datasets such as ECG, EEG, and EMG recordings. Unexpected artifacts, unknown signal sources, and patient-specific variability challenge algorithms designed for automated diagnosis or therapy guidance. Machine learning enhances these capabilities but introduces opaqueness and susceptibility to overfitting, particularly in heterogeneous clinical populations. Drug delivery systems marry chemical engineering and material science, designing carriers that release therapeutics precisely over time and at target sites. Yet the complex in vivo environment involving enzymatic degradation, immune clearance, and transport barriers leads to unpredicted pharmacokinetics. Nanoparticle interactions with cellular membranes and protein coronas are poorly understood, complicating optimization of efficacy versus toxicity trade-offs. Similarly perplexing are phenomena in cancer mechanobiology, where the mechanical properties of tumor microenvironments differ markedly from healthy tissue, influencing cellular invasion and drug resistance. The causal relationships and optimal intervention strategies remain elusive, representing a frontier for therapeutic innovation. Mechanical circulatory support devices, such as ventricular assist devices, VADs, and artificial hearts, face challenges rooted in hemocompatibility. Blood-material interactions can lead to clot formation, hemolysis, or immune activation unpredictably despite sophisticated design. Microscale flow dynamics and biochemical reactions under pulsatile conditions defy full simulation and experimental replication. Rapid advances in tissue and organ bioprinting display promising potential, yet grapple with unforeseen challenges regarding vascularization, cell viability, mechanical integrity, and long-term functionality. Layer-by-layer deposition techniques reveal anisotropies and interfacial weaknesses, critically impacting performance. Emerging fields such as synthetic biology and personalized medicine blend engineering with genetic manipulation, offering tailored disease modeling and therapies. However, complex gene-environment interactions and cellular networks induce nonlinear responses difficult to predict or control, raising scientific and ethical quandaries. Biomedical ethical engineering considers questions posed by augmented cognition, privacy of neural data, and anthropomorphic empathy in assistive devices, navigating uncharted socio-technical territory. State-of-the-art research employs in vivo imaging, multiomics data integration, single-cell analysis, and computational modeling, spanning molecular to systemic scales, opening new understanding pathways, but also revealing deeper biological complexity and engineering challenges. The mysteries within biomedical engineering serve as a humbling reminder of the extraordinary complexity of life. They inspire the relentless pursuit of knowledge, demanding creative engineering solutions, grounded in interdisciplinary science, to push the boundaries of healthcare, improve quality of life, and ultimately unravel the profound secrets of human biology. Data science and machine learning (ML) have revolutionized the landscape of modern engineering, offering unprecedented capabilities for understanding complexity, optimizing systems, and automating decision-making processes. Yet, amidst the remarkable achievements and rapidly expanding applications, these powerful methodologies harbor cryptic behaviors, unexplained phenomena, and fundamental limitations that challenge both practitioners and theorists. This chapter ventures deeply into the labyrinth of mysteries at the convergence of data-driven analytics, artificial intelligence, and engineering, revealing puzzles that continue to confound understanding and inspire innovation. At the foundation lies the paradox of algorithmic opacity. Deep learning models, powering many state-of-the-art applications across computer vision, natural language processing, and control systems, operate as complex, nonlinear function approximators, with millions of parameters. Their efficacy derives from vast data and training, but understanding why they make specific decisions remains elusive, often described as a black box. Despite ongoing development of explainable AI XAI techniques, including attention maps, feature importance scores, and surrogate models, the interpretability of deep models is incomplete and context-dependent, leaving crucial trust gaps in critical engineering domains such as autonomous vehicles, medical diagnostics, and fault detection systems. Deciphering the internal logic of these models, distinguishing artifact correlations from causal relationships, and ensuring reliable understanding of their behavior remain open and active research frontiers. Closely entwined is the phenomenon of generalization failure and unpredictability in machine learning models. Models trained on specific datasets frequently fail when applied to slightly different domains, input distributions, or adversarially perturbed data. This domain shift or out-of-distribution problem signifies a profound limitation of current learning paradigms that assume stationarity of data generation. For engineering applications requiring high reliability, such as structural monitoring, fault prediction, or robotic navigation, unanticipated failure or misclassification due to unmodeled input variability poses both technical and ethical challenges. Despite efforts in domain adaptation, transfer learning, and robust training, achieving truly generalizable and trustworthy ML engines remains a deep mystery. The phenomenon of adversarial examples further exposes vulnerabilities, where imperceptible input perturbations cause radical failures in prediction, classification, or control. Although mathematically characterized in certain scenarios, the origins, pervasiveness, and defense mechanisms for adversarial brittleness remain incompletely understood. The implications for safety-critical engineering applications, where such perturbations could induce physical system damage or catastrophic failures, raise urgent open questions, integrating cybersecurity, numerical analysis, and system design. In optimization for engineering design and control, machine learning introduces another enigma in the form of multi-objective trade-off identification and solution landscapes riddled with local minima. Traditional gradient-based methods often struggle in these rugged, high-dimensional spaces, prompting adoption of heuristic meta-heuristics such as genetic algorithms and particle swarm optimization, whose convergence properties, performance guarantees, and failure modes are empirical and not fully mathematically characterized. Understanding the geometry of these optimization spaces and guaranteeing solution robustness in real-world heterogeneous environments remains largely phenomenological. The management of uncertainty and noise in sensor data and system modeling complicates ML applications. Sensor measurements, experimental results, and operational data introduce stochasticity, missing values, and spurious correlations, confounding model training and inference. Bayesian methods and probabilistic graphical models attempt to incorporate uncertainty directly, yet scaling these approaches to high-dimensional complex systems with real-time constraints is an ongoing engineering puzzle. Scaling data analytics to big data ecosystems exposes engineering complexities related to distributed computing, fault tolerance, data heterogeneity, and privacy preservation. Systems must process streams of data collected from interconnected IoT devices, cloud platforms, and edge sensors while guaranteeing low latency and high availability. Architectures combining batch and stream processing, microservices, and container orchestration operate in environments where unpredictable failures, network latency spike events, and data corruption force complex trade-offs and adaptive mechanisms, whose comprehensive analysis remains a work in progress. Reinforcement learning RL, heralded for its potential in adaptive control and autonomous decision-making, involves another suite of mysteries. Sample inefficiency, exploration-exploitation balance, delayed reward attribution and policy convergence in continuous, stochastic, and partially observed environments, present profound theoretical and practical challenges. RL agents sometimes develop unexpected, unsafe, or deceptive behaviors, exploiting flaws in reward functions or environmental assumptions, exposing fundamental alignment and robustness problems that are still poorly addressed. The extension of ML into cyber-physical systems, CPS, integrating physical processes monitored and controlled via computational algorithms, introduces intricate dynamic feedback loops and emergent behaviors. Understanding and predicting instability, oscillations, or unexpected system-level failures in these tightly coupled networks require new theories blending control engineering with data-driven pattern recognition. Ethical and societal implications intertwine deeply with these technical enigmas. Bias in training data and model outputs, privacy concerns, and the transparency required for public trust remain contested issues demanding integration of engineering rigor with ethical foresight. Explorations combine rigorous mathematical analysis, novel algorithmic frameworks, experimental verification, and system-level deployment studies to advance comprehension. Interdisciplinary collaboration encompassing computer science, engineering, statistics, cognitive science, and ethics fuels progress. In summation, while data science and machine learning unlock unprecedented engineering capabilities, their mysterious facets challenge practitioners to balance innovation with caution, understanding with trust, and automation with accountability. Illuminating these mysteries is pivotal to harnessing the full transformative power of intelligent systems shaping the future of engineering and society. Safety engineering stands as a critical pillar within the vast architecture of engineering disciplines, dedicated to safeguarding human life, protecting assets, and preserving environmental integrity amidst the increasing complexity and scale of modern engineered systems. This domain rests on principles of risk assessment, failure prevention, real-time monitoring, and resilient design. Yet beneath the surface of established methodologies lie profound and persistent mysteries, unknown vulnerabilities, failure modes, and emergent risks that continue to challenge assumptions and compel ongoing vigilance. This chapter offers a sweeping and detailed exploration of the enigmatic challenges defining safety engineering in the robotics, infrastructure, energy, transportation, and complex system domains. The foundation lies in systematic hazard identification and risk assessment, vital processes designed to anticipate possible failure modes, evaluate their likelihood and consequence, and prioritize interventions. However, risk analysts regularly confront unknown unknowns, failure mechanisms, or event sequences not previously observed or modeled. These blind spots stem from inherent system complexity, cascading interdependencies among components, and the nonlinear propagation of disturbances. Methods such as fault tree analysis, FTA, failure mode and effects analysis, FMEA, and layer of protection analysis, LOPA, provide structured frameworks, but by design rely on pre-identified fault scenarios, limiting their ability to foretell entirely novel failure pathways. Safety by design approaches weave principles such as redundancy, diversity, fail-safe mechanisms, and inherent material properties directly into system architectures to mitigate risks. Nonetheless, emergent system vulnerabilities sometimes arise unexpectedly from intricate interactions among subsystems. Software glitches, coupled with sensor noise, timing mismatches within cyber-physical loops, or rare combinations of environmental stressors inducing unforeseen material fatigue. These emergent failures defy simple cause-effect chains, necessitating continual model refinement and interdisciplinary collaboration between systems, engineering, materials science, and computer science. Real-time monitoring systems are indispensable for early fault detection and proactive maintenance. Sensor arrays measure temperature, vibration, pressure, chemical emissions, strain, and other key parameters distributed throughout systems such as power plants, aircraft, bridges, and manufacturing lines. Yet engineering teams encounter puzzling challenges in interpreting sensor data influenced by noise, drift, environmental perturbations, and sensor degradation. Developing robust anomaly detection and fault diagnosis algorithms that minimize false positives without missing early warning signs remains an elusive goal. Moreover, integrating disparate sensor types into a coherent diagnostic framework amid massive data volumes demands advanced signal fusion and machine learning techniques still being perfected. Human factors introduce an additional unpredictable dimension to safety. Errors in operation, maintenance, and design ranging from slips and lapses to systemic organizational failures intermingle with technical faults amplifying risk exposure. Human reliability engineering attempts to measure, predict, and mitigate these risks through ergonomic design, training, and procedural controls. Yet the inconsistent and situational nature of human behavior defies deterministic modeling, requiring behavioral science and cognitive psychology inputs complemented by engineering rigor. Cybersecurity has emerged as a new frontier, where safety engineering extends to defending control and monitoring systems against intentional attacks, hacking, and sophisticated cyber-physical threats. This domain combines classical safety risk with information security considerations, creating complex attack vectors where breaches can induce physical damage or operational disruption. Designing secure-by-design architectures with intrusion detection, resilient control, and fail-safe failover reveals deep unsolved problems integrating software engineering, cryptography, control theory, and risk management. Emergency preparedness and resilience engineering deal with the capacity of complex systems to absorb, adapt to, and recover from unexpected disruptive events, natural disasters, human-induced failures, or cascading technological breakdowns. The dynamics of resilience exhibit nonlinearities and feedback loops where small perturbations grow into large-scale failures with wide-reaching consequences. Modeling such scenarios goes beyond static risk quantification, incorporating real-time data analytics, simulation-based scenario planning, and hybrid human-machine decision processes, fostering adaptive response. Environmental conditions, social networks, infrastructure redundancies, and organizational factors all interplay in ways not fully captured by existing frameworks. Regulatory frameworks and safety standards such as ISO 31000, IEC 61508, and industry-specific codes enforce compliance but often lag behind rapidly evolving technological landscapes and emerging risks. Adapting regulatory paradigms to dynamic, software-intensive, and data-driven systems embodies both a policy and engineering challenge, demanding forward-thinking innovation. Novel technological domains such as autonomous robotics, AI-controlled cyber-physical systems, nanotechnology, and additive manufacturing introduce fresh unknowns in hazard identification and mitigation. Understanding potential failures from novel material properties to algorithmic decision errors requires extending safety engineering into multidisciplinary and speculative foresight activities. Research advances couple digital twin technologies, virtual replicas of physical systems simulating real-time condition and prognostics, with AI-driven safety management platforms enabling predictive, prescriptive safety actions before failures manifest, promising a shift from reactive to truly proactive safety assurance. This comprehensive panorama affirms that safety engineering, while anchored in tradition, is a continuously unfolding frontier, confronting mysteries across scales, disciplines, and domains. It demands a holistic, adaptive, anticipatory approach integrating technical excellence, human factors, ethical responsibility, and continuous learning to protect increasingly complex engineered systems in an uncertain and evolving world. As the culmination of this extensive exploration, Part 16 synthesizes the myriad engineering mysteries uncovered throughout this series, melding insights from structural anomalies, fluid dynamics, material science, electronics, robotics, energy systems, biomedical innovations, data-driven technologies, and safety engineering into a panoramic view that reveals profound interconnections and overarching themes defining the current frontiers and future horizons of engineering. One of the striking consistencies is the persistent presence of complexity and multi-scale interactions as fundamental sources of unpredictability. Across engineering disciplines, whether examining turbulent flow vortices, cascading across scales, crack nucleation stemming from atomic dislocation motions, or emergent traffic congestion arising from collective human behavior, the entwining of phenomena spanning atomic to systemic dimensions challenges reductive, isolated modeling approaches. This systemic complexity embeds nonlinearities, feedback loops, and stochastic variability that traditional deterministic frameworks struggle to contain, necessitating new paradigms embracing uncertainty, emergence, and adaptive control. Another unifying thread is the intrinsic limits of measurement and observation tools across domains, from nanoscale material characterization to real-time sensor networks monitoring infrastructure. Imperfections and noise obscure signals and introduce ambiguities, limiting situational awareness. Efforts to enhance sensing resolution, deploy multiphysics tomography, and leverage artificial intelligence for signal interpretation progressively chip away at these barriers, yet fundamental epistemic uncertainties remain inherent, shaping engineering judgment and risk tolerance. Emergence of novel materials and fabrication techniques introduces phenomena absent from legacy systems, but frequently unforeseen due to incomplete knowledge of multi-scale physics, chemistry, and interfaces. Additive manufacturing creates microstructural anisotropies, complicating fatigue life. Quantum materials exhibit topologically protected states, defying classical predictions. Nanomaterials present size-dependent anomalies. These innovations demand continual adjustment of design principles and standards, resisting one-to-one digitization of historical knowledge. The rise of artificial intelligence and data science reshapes engineering methodologies, but brings new mysteries, opaque decision processes, vulnerability to adversarial perturbations, and difficulties in generalization temper euphoria with caution. This convergence of prediction, control, and optimization under uncertainty invites deep collaboration among statisticians, computer scientists, engineers, and ethicists to cultivate trustworthy, explainable, and equitable technologies. Environmental and societal contexts permeate all facets of engineering mystery. Climate variability, urbanization, resource depletion, and regulatory dynamics introduce external forcings that modulate material behaviors, system loads, and human interactions in unpredictable manners, complicating planning and design assumptions. Safety engineering emerges as an indispensable integrative discipline, confronting multifactorial risks and unknown failure modes through proactive hazard identification, vigilant monitoring, resilient system architectures, and ethical stewardship, transforming mystery into managed uncertainty and safeguarding societal welfare. Underlying these technical mysteries is the human element: cognition, creativity, adaptability, and fallibility. Understanding human factors within complex engineered systems remains an active and essential dimension to elucidate, from operator error in control rooms to user acceptance of autonomous systems. Future investigation demands multidisciplinary, quantitative, and holistic approaches combining high-fidelity experimentation, advanced modeling, real-time sensing, and machine intelligence enhanced by transparent human oversight. Emerging digital twin platforms simulate entire systems integrating physics, data, investment in education, fostering systems, thinking, data literacy, and ethical frameworks is critical to prepare engineers capable of navigating and mastering the interwoven mysteries of contemporary technologies. In conclusion, the panorama of engineering mysteries reveals a dynamic landscape where known laws interplay with emergent phenomena, measurement constraints, and evolving socio-technical paradigms. This terrain offers immense challenges and unparalleled opportunities to deepen scientific understanding, push technological boundaries, and design robust, adaptive, and sustainable engineered systems that enhance human well-being. Thus, embracing and illuminating the unknown becomes essential, not as a retreat from rationality, but as the essence of engineering innovation, melding curiosity, rigor, and humility to engineer a resilient future out of the mysteries that captivate and confound us.